Today we're going to take a look at how atoms hybridize, that is to say, how they take their atomic orbitals, like we studied before, the 1s2, 2s2, 2p6, and what they do as they go about making molecules. So if you look at the right-hand side of this slide here, this is what you start with on the left, 2s with 2 electrons and 2p with 2 electrons for carbon. And this is what you end with over here on the right. Or if you look at the pictures, you might remember the balloons that we used. You start off with what's on the top here, this red orbital and these 3 green orbitals. That's what you start with, and you end with these ones on the bottom, which ends up making a molecule that looks like a tetrahedron. So let's get started. The first thing you want to do is remember what the heck AOs are, or atomic orbitals. So there are 3 examples for you right here on the left side. There's boron, 1s2, 2s2, 2p1, and I know that because boron is found right here, and it has 5 electrons. We also drew them, so they look like this on the right side. 1s with 2 electrons here. I'm circling them right now. 2s with 2 electrons, and the 2p with 1 electron. Now let's look at what happens when those atoms produce molecules, like we've seen oh so many times. Methane is this molecule here. What happens as it bonds? So there's carbon in the middle with a hydrogen, 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 hydrogen. So you know that it has 2, 4, 6, 8 electrons in its outer shell after it's bonded, because it starts with 4 and it gets another one from this hydrogen, another one from that hydrogen, another one from this, another that, and it has 8, an octet. And we would write the AOs as 1s2, 2s2, 2p2. We also know the molecule is tetrahedral, right? So it has 4 sides, 1, 2, 3, 4 sides. And the bond angles are 109.5 degrees or so, and its geometry and its shape are the same because they're all shared pairs of electrons. So what happens during hybridization? Right here it says valence orbitals hybridize to form 4 identical sp3 hybrid orbitals. So if you think of hybridization, you might have one kind of cow and another kind of cow hybridized. You probably should write down what's in the bottom left-hand corner, what's in red here. You make the AOs, and then you promote electrons if necessary, and then you rewrite the orbital name and redraw them if you're asked to do that. Alright, and another thing is on the bottom right hand corner in red again is something that you should probably write down. Orbitals and electrons are conserved. That is to say, you don't lose or gain a certain number of orbitals or electrons. Let's take a look at the top right here. This is carbon. What we don't see is the 1s, because the 1s are not, I'll just draw them here for a second. 1s2, okay, so those are not in the valence shell, and so we don't bother with those. We just care about the ones in the valence shell, the second PQN. So we have 2s2 and 2p2. This is what we start with. These are the atomic orbitals. Whoops, kind of overdid that. And then over here are the hybridized orbitals. So notice that we started off with 1, 2, 3, 4 orbitals, and we end with 4 orbitals as well. 1, 2, 3, 4. Now one thing happened we haven't talked about yet, and that's called promotion. So what we do is we take this 1 electron here and we put it up here into this empty space. So we try and get all the orbitals having 1 electron, and that was the Hund's rule, wasn't it? So we put this 1 electron up here, we give it an upward spin, and so we take all 4 of those orbitals and we put them over here on the right side. All right, and they all have 1 electron in them. So they're hybridized right now. So what do we call these things? Well, we call them sp3 hybrid orbitals. sp3, and it's really easier than you think. The sp3 hybrid orbitals are made out of 1s and 3 p's. So 1s and 3 p's. Let's erase this so we can see again. It's made out of this and those 3. So that's why it's called sp3 hybridization. And notice the energy here is, if we go over to the left axis here, it's somewhere between the s's and the p's. And this also shows us about what's going to happen when bonding occurs. Because if you look back at the molecule again, so along comes hydrogen with an electron, and pretty quick we'll have 2 electrons, so this would be a downward one, Pauli exclusion principle. And then our second hydrogen comes in, we get another electron there, third one, and fourth one. And that is why we end up with 4 identical hybrid orbitals here. No, we're not going to draw these very much, but it might help you, especially if you're a sort of a visual learner. If you look at the bottom right, so we start off with the S and the three P's, and they look like this. And then we hybridize them, and they all end up looking the same. And they all end up poking out of that central carbon atom. Next page. All right, let's take a look at another example. What is the hybrid bonding arrangement for nitrogen, the central atom, in the ammonia molecule? Periodic table tells us that nitrogen has 7 protons in the nucleus, right here. And so we would have 7 electrons in the shells, 2 in the first shell and 5 in the second shell. But usually, for the purpose of hybridization, we want to use the Schrodinger model, which is this one over on the right. We would write 1s2, 2s2, 2p3. So the 1s's, we don't really care about those because those are not valence electrons. Okay? The hybridization is going to happen among the 2s and the 2p orbitals. All right, what else do we know about NH3? Well, let's see. It has tetrahedral geometry. It has trigonal pyramid shape, and it has an unshared pair of electrons, and the bond angle should be about 109.5 degrees. Now, if you look at this diagram in the center, it says the bond angles are 107, and that's because VSEPR tells us that this pair of electrons here, this unshared pair of electrons, really is repulsive, so it pushes these other shared pairs of electrons away, so the bond angles are a little bit less than 109.5. So let's take a look at what you should be able to do. These are the AOs, what happens before, for nitrogen in ammonia. Don't care about these ones because they're not valence electrons. Hybridization occurs in taking all 4 of these orbitals and making new ones. And the energy of these is between the energy of the 2s and the 2p. And the orbitals are conserved. We started with 4, we end with 4. The electrons are conserved. We started with 1, 2, 3, 4, 5, and we end with 5. Wasn't so hard, was it? Let's take a look at some of our favorite atoms and molecules. Let's try beryllium. So there are 2 ways to look at this. We can do this in the picture method here with the green orbitals, or we could do it with the orbital model with the boxes up here. So beryllium, what do we know about it? Well, Be is a weird atom. It likes to have 4 electrons in the outer shell. It starts off with 1s2, 2s2, and 2p0. I'm trying to point out that those p orbitals are there even if they're not occupied. When we put them together, the 2s and the 2p's, they hybridize, and we make hybrid orbitals. We take an electron and we promote it up here to the 2p. So here you can see it right here. And then we hybridize it. So this orbital, the 2s, and this orbital, the 2p, hybridize to make two sp orbitals. Why are they called sps? Because they're made out of an s and a p. Let's try boron. So look at your periodic table, and you'll see that boron has 5 electrons. 1s2, 2s2, 2p1. It ends up being a trigonal planar molecule with 120-degree bond angles. And what happens? So let's look over on the right side. It starts off like this: 2s2, 2p1. We'll take 1 electron and promote it up here. Okay, so far so good. This is after promotion, and then we're going to take these 3 orbitals, all 3, and hybridize them and make them all have the same amount of energy. Each one in this case has 1 electron in it, and it's ready for bonding. It's ready to make 3 bonds because you can see that there's room for 3 more electrons. All right, and then the last one we'll look at is carbon. So carbon starts off with 6 electrons, 1s2, 2s2, 2p2, and then it hybridizes to make the familiar tetrahedral shape, 109.5 degree bond angles. This is what you start with. We know that we want to end up with 4 orbitals, right? And so we'll take one of these electrons and promote it up here. So now after promotion, we're looking at this, and then the last thing is we hybridize. In other words, you take all 4 of these orbitals and make them have the same amount of energy, so they're going to be identical. And the last thing I'd like to point out to you is that we could extend this even farther, look at some bigger atoms. So let's take a look at this one over on the left here. There is an atom out there that takes a 5s and it's 1, 2, 3, 5p's, and 2, 5d orbitals. So 2, 4, 6, 8, 10, 12. It can have up to 12 electrons in its outer shell. Now this atom is called sulfur, and it can have 12 electrons in its outer shell, and think it has a full outer shell. What would you call the hybrid orbitals that are made up of an S and a P and a P and a P and a D and a D? You call it sp3d2. That would be the hybridization, and there's room for 12 electrons, 2 in each orbital. All right, this bottom one down here, let's take a look at this. Here's an atom that takes 1, 2, 3, 4, 5 orbitals and hybridizes them, having room for 10 electrons. That one would be, I think I have it here. There it is. That would be this one right here. So 1, 2, 3, 4, 5 orbitals, room for 10 electrons. That's bigger than an octet, but still the atom is happy about this. All right. So a couple more practice problems over on the right. How many atomic orbitals make up 2 sp hybrid orbitals? The answer is 2, because they're conserved. How many atomic orbitals make up 5 sp3d hybrid orbitals? Well, 5. An S and a P and a P and a P and a D. So that's 5. All right. Another question. If sulfur can have 6 bonds, 6 pairs of electrons in the outer shell, what must its hybridization be? So it would need 6 bonds. It would need 6 boxes, 6 orbitals. Is that 6? I think that's 6 right there. So this one would be made from an S, this from a P, this from a P, this one from a P, and a D and a D. So the answer is S, P, 3, D, 2 is the answer. All right. First we had a little refresher on atomic orbitals, and then we started looking at the steps that we need to take to make hybrid orbitals. That is to say, make your AOs, promote electrons if necessary, and then put all the atomic orbitals together to make hybrid orbitals. And it's kind of the same thing over and over again. It just takes practice, but you guys always dominate this. That's our lesson for today. Make sure that you stop in and ask for help if you like. And thank you very much for watching.